All right, good afternoon, everyone. My name is Zhiju. I'm going to present our work, WtaGraph, web tracking, and advertising detection using graph neural networks. This is a joint work with Weiping, Monchu, and Chuan. All right, so what is web tracking? Well, when we are visiting a web page, behind the scenes, trackers are collecting our browsing information. And well, it turns out web tracking is performed on the vast majority of the websites, according to different measurement studies. Well, why would they do that? Targeted ads and the site analytics. Right behind the targeted ads is like large business markets. Okay, how do they do that? Cookies definitely is the one, and it's a widely used one. Also, some advanced techniques such as browser fingerprinting, device fingerprinting, sensor fingerprinting, canvas fingerprinting, you name it. Okay, so basically with web tracking, we see it is like a compromise of our privacy. As sad as this dog over here, we don't want being tracked. Okay, so what we can do? Well, as a web user, you can use browser extensions such as AdBlock, uBlock, AdBlock Plus, so on and so forth. Those are all filter list-based solutions. And in recent years, we have machine learning-based solutions such as AdGraph, normal ads, right, and a few more. So here, there are some limitations with both solutions. For example, with the first one, filter list-based solutions, you have a rule-based. You're going to spend a lot of effort to manually maintain the filter list. And here, with the machine learning-based solution, there's still, performance-wise, there's still a lot of room to improve. That's why in this work, we want to have a better tracking and advertising detection to help out this dog over here and to also protect ourselves. Okay? So with this goal, we have like a rather straightforward intuition. That is, we can have a graph to represent the web traffic, where we have the nodes representing the domains. And in between those nodes, we have edges representing the HTTP traffic. And with this graph, we can formulate the task of detection to be as edge classification. So basically, you have a graph over here, and you have two types of edges, the green one and the red one. Either it is tracking or non-tracking. It's a binary classification. All right? So more formally, we have this attributed homogeneous multigraph, where you can reference the web traffic. And as you can see, you can associate different features or attributes to the nodes and edges. And also, in between those different nodes, you can have multiple edges, which is very realistic nowadays with web traffic. And then formally, the task will be the edge representation learning and classification in such a graph. Well, we pick up GNN, which is graph neural network. It is because it's really a great choice for this type of task. We have like a graph structured data over here. And also, GNN is known for its like neighborhood aggregation, also known as message passing. So that mechanism can leverage and learn the implicit feature of the graph structure. So with different works, papers, projects, they have shown that graph neural network can outperform traditional machine learning a lot. Okay? All right, so this is our formulation, and this is our intuition. So with that, we implemented WtaGraph. So over here, we have like 4 components. We have a data collector. Basically, it's like a browser extension. We use that to collect HTTP traffic and other data. And then the second component, we have the data collector, where we can build the graph from the collected data. Meanwhile, we can also extract the features. So like the character embedding, statics of the URL, and the DOM, so on and so forth. Continue, we have our unique WTNGNN over here. So it can directly work on our attributed homogeneous multigraph. So basically, with this, we train the model, and correspondingly, we have the last component that can classify whether an edge representing HTTP traffic is tracking or not. All right? So as you can see here, we have 2 different settings, transductive setting and inductive setting. So for the transductive setting, here we assume that we have all the data ready. Basically, we build a graph, and then we do the prediction, I'm sorry. So application scenario for this could be you want to have filter list generation. You want to generate rules. And then on the bottom part, we have the inductive setting, where it's kind of more realistic. That is, you train a model, And later, you got a new edges coming in. You're going to present those unseen edges. Okay? So the more realistically, you can have the real-time detection, right? And I want to give a little bit more details regarding how do we learn the edge representation with our graph neural network. So it is learned by aggregating the neighborhood node representation plus the neighborhood edges representation plus its own representation. Just like here in this simple graph, let's say our target edge is the green edge. The representation is learned by incorporating itself, its own representation, plus the source nodes and destination nodes, plus the neighborhood's edges. Okay? This is how we learn the edge representation. And to continue, we have the algorithm. I will not spend time on explaining this. You can read more in our paper. So here we implemented this WtaGraph, and now we want to check, hey, how well does it perform? We have different evaluation experiments in 2 different settings, like here in the transductive setting. So first of all, introduce our data set. We use our data collector. We collected 1.5 million requests from Alexa top 10K websites. And using filter lists, we labeled 39% of them as tracking, or we are in short like WTA. And recall a little bit with transductive setting, what we want to do is that we observe all the data, and we build a graph, we train the model, and we predict the edges. So what we do over here is that we predict the edges with tenfold cross-validation. So this is the performance table summarized it. Here we have 2 baseline models. Well, technically 3. So here the first one, which is the link prediction model. This is one of our baseline models. The idea with this one is that you learn the edge representation by averaging the source node and destination node representations. So this works well with a simple graph, but recall here we have a multi-graph. So as you can imagine, as you can see from these numbers, it doesn't perform that well. And continue, we have MLP, classic neural network, but for this one, there's no graph involved at all. Continue next, in the third one, we have our advanced link prediction. Basically, for this one, the idea is more like, hey, incorporating its own edge representation with the node representations. But for this one, if you compare with our final version, there's no neighborhood edge aggregation. Okay? So as you can tell from these numbers over here, definitely WtaGraph works very well. And several messages behind these numbers. First of all, without a graph, let's check the MLP. The numbers for MLP, really, you compare that with the third and the fourth one. Without a graph, without a graph neural network, the performance is a little bit worse. And also, if you compare the last 2, which all of them are our models, you can see that neighborhood edge aggregation really helps to improve the performance. Okay? Continue, we have this. You might wonder in the previous slides, hey, you use filter lists as a ground truth to label your edges. This is a concern, right? And you might don't agree with that, because in fact, what you want with this work is that you want WtaGraph to identify trackings that are missed or not included by filter lists. So this is something we want. We want to go beyond filter lists. Well, to address and to evaluate this concern, we did a lot of manual verification. We in total sampled like over 4,000 requests. Here we have some results. For example, we sampled those false positives and we manually verified. So for false positives, that is, filter lists consider those requests as non-tracking. But our WtaGraph classifies them as tracking. So for a case like that, we verified that around 40% of the time, WtaGraph indeed is correct. So which means it can detect tracking that are missed by filter lists. Continue for the false negatives, which means like the filter lists consider them as tracking, but our WtaGraph here classifies them as non-tracking. For a case like that, around 70% of the time, we are correct, which means filter lists incorrectly labeled them as tracking. And the WtaGraph over here can recognize, all right, you did something wrong. Okay? So basically here, we have more like experiments results in the paper. You can refer to the paper for details. But here, as you can see, indeed, WtaGraph can do more than filter lists. Okay. Continue. Here, recall we have the second setting, which is inductive setting, which is a more realistic one, where what we want to do is that we want to have a pre-trained model to predict the traffic, to predict the request that has never been seen during the training phase. Here, we train 4 models on graphs with different sizes, and then we evaluate on the rest unseen websites with unseen web pages, unseen requests. So here is the performance. This figure over here summarizes the performance. On the very left, we have the WtaGraph in the transductive setting for comparison. As you can see, here basically the message is that, for example, with this random 7K model, that is, we train the model with a graph, build it with 7K website traffic. So with that, the performance accuracy is like 98%, precision 98%, and the recall 96%. It's very close to the model in the transductive setting. But as you can tell, like the larger the graph, the better performance you will have. Okay. So continue. We want to evaluate, hey, how robust is it? Is it possible to evade your detection? Well, we consider 4 evasion detections. Considering here we have a tracking URL, and the tracker could change the second level domain, like the add CDN over here. So it can change that. Meanwhile, it can also change the lower level domains. For example, change the add or serve at the very beginning. And also, how about they expand the URL length? Because here in this work, we truncate the URL at the length 200. We want to figure out whether that is a problem or not. What if the URL is larger than 200 characters? Continue. The trackers can also replace those sensitive keywords, like the tracking in the past. You can see they can replace that with non-sensitive keywords. Here, this table summarizes the successful evasion rate against our WtaGraph. For example, here with the first evasion technique, changing the second level domain, around 3% of the traffic can successfully evade our detection. For comparison, that for the filter list, that will be over 57% of the traffic can successfully evade the detection of filter list. But it is reasonable because filter list over here is more like a rule-based. They have hard-coded domain names in their rules. So that's why if the trackers change their domain name, it is reasonable that they can evade those detection. All right. A quick sum up. So here our goal is that we want to have tracking and advertising detection. And the intuition is rather straightforward. We want to have this graph to represent the web traffic, and in which the nodes represents the domain and the edge represents the request. And we formulate this detection task as an edge classification problem. It's a binary classification. And then we design and build this WtaGraph. One of the key components is the WtaGraph neural network. And it does the work excellently. All right, so this is pretty much all what I have for you. And you can read more in our paper, or you check our released source code on GitHub. I'm happy to take any questions now.
Thank you, Zhiju.
Thanks.
We have questions.
So I have a quick question. Did you also compare real-time performance of this with the previous work, and which one was better?
Yes. This is really great. We have that. We have the real-time performance evaluation. So basically, what we did is that we leveraged the Google Chrome native messaging. Basically, we run our WtaGraph in the process, and we have our browser extensions to communicate with our WtaGraph. And the overhead, time-wise, it takes like 266 milliseconds per web page, well, among which 100 milliseconds is used for message exchanging, and 166 milliseconds are used for prediction, constructing the graph and do the prediction. Yes.
Hi, I was wondering if you can give us more intuition about why you chose your graph structure versus just using GNNs on the provenance-based graph for AdGraph?
If I understand your question correctly, so basically here we have, so the intuition is more like we can have a graph to represent the traffic. And meanwhile, we learned graph neural networks really is a great choice for this kind of task. That is, you process graph structured data. That's why, combine everything together, we decided to go with graph neural network. However, some existing graph neural networks, they cannot handle our graph. Recall, we have attributed homogeneous multi-graph, and existing models cannot handle that. That's why we designed our WtaGraph neural network. Did I answer your question?
Yeah, thanks.
Okay, great. Yes.
Yeah, so my understanding of the labels here on the edges is that they're the URLs. And I'm curious whether you think that there's any utility or potential in also considering the payload contents.
The payload contents, for sure, no, we did not consider that. It's more from the overhead perspective. We have that kind of concern. We do not consider that.
Okay, cool. Thanks.
Yes.
So if I understand your project correctly, your graph neural network is trained on the training data set labeled by the filter list, right?
Yes. Yes.
And in that case, you can still identify or detect some WTAs missed by the filter list.
Yep.
So could you share more insight about this result? Because basically, if you just you can outperform the labeled data set, right?
Yes.
So yeah.
Okay, so let me explain this way. You consider because here we have a graph, and from the labeling perspective, manual labeling perspective, because you're gonna prepare your filter list, you have a bunch of rules, right? That's manually maintained. Well, if that is an image, it's easy to create a rule. Hey, say an image for that URL should be blocked because that is for tracking or for advertising. So rules with that, with explicit resource, it's easy to create it. However, for those implicit or like those hidden traffic, it's really hard for people to label them and create corresponding rules. But with our graph neural network, with that graph structure, because all of those, no matter it is like a visible or invisible resource or traffic, they all send to the same nodes. That's why we can learn, all right, even though this is invisible, we can still identify that, still detect that. That's something filter list cannot do very well.
So you mean that the graph neural network can learn the implicit signals that are even invisible in the training labels?
Yes, if that is not labeled by the filter list, basically by the human behind.
Okay, thanks. I have another quick question. So,
Yes.
so you mentioned that you have two settings, right? The second one is the inductive setting. Basically,
Yes.
you need to handle some out of vocabulary request, right?
Yes.
So in that setting, do you need to retrain your model to predict the links for these unseen URLs, or?
We do not need to retrain. That's why we want to have that, so that it doesn't matter. We train that on the previous graph. Now we can handle the new unseen edges. That's why in real time we have that kind of performance, 266 milliseconds delay. Because if you want to retrain, and that will take a lot of time. But you can definitely regularly retrain to achieve the better performance consistently.
Okay, thanks.
Yes.
Omar, University of Washington. So one thing that AdGraph did was it tried to classify as the web page was rendering.
Mm-hmm.
So some of the nodes would have different graph properties and they will like improve over time. So are you doing the same thing in WtaGraph?
So I guess you're talking about like the features for our graph, right?
Yeah, so basically features were built as the web page was rendering. So at one point in time when you have like very few nodes, the features would have a lot less or smaller values, and as the graph would build, they will have higher values, for example.
Yes, we will have that. So basically we have different categories of features: character embedding, JavaScript API access, and there's URL statics, and the DOM, so on and so forth. It's all basically all inspired from the previous related work.
Right.
Mm-hmm.
Thank you.
Mm-hmm. Yes.
Just a quick one.
Hi, this is Pune from UC Davis. I was wondering, as your threat model, do you also consider cases when the third party or tracker collude with the first party, when they hide their content, like using like CNAME cloak?
Yes, that's a really great question. Like first-party tracker versus third-party tracker. Well, in this work, we do not differentiate. As long as it is tracking, we just block it. We won't detect it and we won't block it. But to make it clear, some information sent to the first-party organizations or sent to the first party, that makes sense because you need that. For example, you want to have credit card information being sent to the server, right, to process your order. For that, we do not consider those tracking.
Mm-hmm.
Okay.
Thank you.
Yes.
Okay, let's thank the speaker again.